A single grain of common beach sand contains enough metal impurities to permanently short-circuit a silicon wafer. If every data center vanished, the path back would begin by boiling quartz in electric arc furnaces at 3,000 degrees. Rebuilding our digital world requires retracing a 300-year chain of industrial steps, where one missing link leaves us in the dark. Surprisingly, a microscopic strand of glass that took 3 decades to perfect is the most fragile link in this chain. Our modern lives rely on these sterile, windowless concrete fortresses that hum with the power of entire cities. Inside them, server racks process the data streams that run our financial networks and artificial intelligence models. We treat this processing power as an infinite resource, yet it is entirely dependent on a delicate, manufactured environment. Once that environment is disrupted, the digital facade collapses in seconds. To understand how hard it is to rebuild, we have to start at the physical foundation. It begins with the most abundant mineral in the Earth's crust, which is also the most difficult to purify. Ordinary silica sand must be transformed into metallurgic-grade silicon by reacting it with carbon in massive furnaces. This produces silicon that is 99% pure, which is clean enough for steel but useless for computer chips. To make a transistor, we need electronic-grade silicon, a material refined to 99.9999999% purity. The purified silicon is melted and pulled into a single, perfect crystal ingot that looks like a metallic cylinder. Engineers slice this cylinder into wafers thinner than a playing card. Then, lithography uses extreme ultraviolet light to print billions of microscopic switches onto the silicon surface. These machines are the most complex instruments ever built, requiring mirrors polished to the atomic level. Building a single chip factory costs over $10 billion and requires a clean room where air is filtered 10,000 times more than an operating theater. Should humanity lose this machinery, we could not simply rebuild it in a standard workshop. Humanity would have to build the tools that build the tools, a regressive loop that could take decades to resolve. But let's assume we somehow succeed in manufacturing the microprocessors. This is where most rebuild attempts would fail. Bare processors are useless without an immense supporting infrastructure. One modern server rack packed with processors consumes more electricity than a typical neighborhood. All that electrical energy is converted directly into heat, which will melt the silicon in minutes if it is not removed. For this reason, modern data centers are giant thermodynamic engines. Such systems require massive cooling loops that circulate millions of liters of purified water every day. Cooling setups use massive evaporative towers and liquid immersion systems where servers are submerged in specialized oil. Without cooling, automated systems trigger an emergency shutdown to prevent the hardware from cooking itself. Keeping these cooling loops and server racks running requires a continuous, uninterrupted flow of electricity. Data centers cannot rely on the power grid, which is prone to fluctuations and blackouts. Instead, they rely on battery banks for backup and rows of diesel generators the size of locomotives. While these generators can keep the servers running for days, they require a constant supply of fuel. Solving the heat is only half the battle. It doesn't solve the distance. Any data center containing billions of processors is a silent island if it cannot communicate with the rest of the world. Engineers connect these islands using fiber optic cables, which are thin strands of glass that transmit data as pulses of light. Here, we return to the glass strand, which must be so pure that light can travel 100 kilometers through it without fading. Picture ordinary window glass as thick as the ocean is deep, blocking all light from reaching the ocean floor. But if fiber optic glass were as deep as the ocean, the bottom would be perfectly visible. Achieving this transparency required decades of research to eliminate tiny metallic impurities and bubbles. Once manufactured, these glass strands are wrapped in protective steel armor and laid across the ocean floor by specialized ships. Over 1 million kilometers of undersea cables connect the continents, forming the physical nervous system of our planet. Cutting this network would instantly fragment the global internet into isolated local networks. Rebuilding this infrastructure would require specialized cable-laying ships and glass-drawing towers. Even if we reconnect the network, the sheer scale of modern computing presents a different kind of barrier. While a single server can run basic software, running a global search engine requires thousands of processors working as one machine. Such scale requires complex distributed software that coordinates millions of simultaneous calculations across thousands of physical racks. Should one server fail, the software must instantly reroute the workload to another without losing data. Writing this software stack took millions of engineering hours, making it just as essential as the hardware itself. Without it, our hardware is just a collection of expensive heaters. The ultimate irony of our digital age is that our most advanced virtual creations require unprecedented physical resources. Indeed, a single modern data center can consume over 100 megawatts of power, enough to supply 80,000 homes. Training a single state-of-the-art artificial intelligence model consumes more electricity than a small town uses in a year. Immense quantities of water are also required, evaporated into the atmosphere to keep the silicon cool. We built these digital fortresses to escape the physical constraints of our world, but they have tethered us to the Earth more tightly than ever. Whenever the servers go dark, we are left with nothing but silent concrete hulls and piles of refined sand. Our modern cloud remains anchored to the Earth, built entirely from boiled quartz and microscopic glass. If this entire digital empire collapsed tomorrow, which physical resource would humanity fail to secure first?